Hello. You are not audible. Still not audible, Kaushik. For 3 to 4 minutes, let everybody join, then we will start.
Okay, sure.
Okay, so it's 6 p.m. right now. We will start from 6 to, let's say. So, yeah, hi everyone. I'm Shatik and I welcome you all to the fifth webinar of E16 classes. And today I have a very talented person. I know him from my bachelor's and he's a very good friend of mine, Kaushik Thakkar. He has done his master's degree from IIT Kanpur and BSc from Ramakrishna Mission Narendrapur. Right now, he's at a very like one of the largest bank in the world as a risk analyst, and so he has a very firm knowledge in his domain. So yeah, without any further delay, I would like to hand over to Kaushik.
Such a great introduction. Thanks a lot. Okay, so let me share my screen.
And so, if you guys have any question, you can ask. Like you can ask him while he's giving the lecture, or you can just give it afterwards.
Okay. I think everyone is able to see this. Can you just confirm once?
Yes.
Hello, everyone. First of all, thanks for joining because it's great that on a Saturday evening you all are here to listen to the seminar. Just two things. Uh, so in this one, we will be basically diving into the basic concepts of pattern recognition and 2 to 3 algorithms that we use in machine learning, and I hope you will like it. And whatever we will be doing, it is just a surface level introduction where we'll get to the basic concepts of the algorithm, not going into too much mathematical details. So if you have any questions, feel free to ask during the session or after the session as well. And the medium of this session will be English and Hindi. I think you all are comfortable in that. And hmm, okay, that's it. Let's get started. So the title is From Data to Decisions. As you can infer from this, basically we have a lot of data. We'll use that to take decisions, and we will be focusing on pattern recognition as okay. So, what pattern recognition is, I would like to start with giving an example. So, for example, you're in a crowded market, and suppose you see one of your friends from the back. I guess everyone is able to recognize him, right? So, just think once, how is this even possible that by not looking at the face, you're still able to recognize a person from his walking style or from his dressing sense or his posture. So this is nothing but the natural ability of pattern recognition at work, right? So this is a cognitive skill set that all the people have. So we tend to recognize patterns in our day-to-day life. They can be recognizing a face, recognizing a person, understanding spoken words, reading handwritten characters, right? And how do we come to have this ability? This is just by our training, that we have done these things over time and we have developed this. So pattern recognition is nothing but the act of taking in raw data and taking an action based on the category of the pattern, right? So now what we are focusing on is, we seek to design and build machines that can recognize patterns as well, right? And this is very interesting, and this is possible by the combination of maths, statistics, and computer science. That the natural cognitive ability that we have of recognizing patterns, we can instill them into machines as well. So machine learning is basically a field that addresses the question of how we can use our historical data to discover general patterns and improve the process of making decisions, right? It has got various use cases in industries like manufacturing, medical diagnosis, finance, sports, and we also use it in our day-to-day lives. For example, search engines, uh, customer adaptive websites. For example, you have seen in Amazon that your product recommendations are based on your buying history and all those stuff. We have email managers, thanks to them, because for them only we are not flooded with spam emails, so they tend to classify emails which are spam, which are not spam, pretty much effectively. And there are many more examples like that. So these are all use cases of pattern recognition. In today's seminar, we will just deep dive into few algorithms of how the machines are able to do this by using a bit of maths and statistics. So for today's session, we will consider an imaginary example, right? Let's say we are at a fish packing plant and we want to automate the process of sorting incoming fish on a conveyor belt according to species, right? So what is happening is there are thousands and thousands of fish coming on the conveyor belt. Now, for a human to sit and classify them is very difficult, because different species of fish are to be packed in different packets and they have to be transported accordingly. So why not automate this process by using machines? Again, as you can sense, this is nothing but an act of pattern recognition that we will do. Suppose you have a fish. So for simplicity, we'll consider a binary task that either it's a sea bass or it's a salmon, right? Now, how do we decide which one is this? Our cognitive ability helps us to decide very easily by looking at the length, lightness, width, a number of fins, and the shape of the fish to decide whether it's a sea bass or salmon, right? And how do we get this ability? By seeing some fish which we are told that it's a sea bass or it's a salmon, right? So the same ability has to be instilled in a machine as well. And why do we care to do this? Because again, it's a huge waste of human resources if some people, this like this work is done manually. This is tedious and very expensive as well. So what happens is, what we are trying to design is, suppose we have an incoming fish, we will capture its image, right? And we will have some feature extractor. For example, our features for us is the length, lightness, number of fins, shape of the fish, right? But when you capture an image, so it's basically numbers, right? So we can design such feature extractors which will identify the prominent features or prominent patterns from those set of numbers and convert it into a list of numbers which are called features. Now these features are given to a classifier, or a person, or a machine that decides based on these features whether this is a sea bass or a salmon, right? So in this seminar, we are not going to look at how these feature extractors are created. This is a different field altogether. This is also domain specific kind of a thing. But what we will look at, suppose we have our features, suppose we have a good feature extractor. Given this feature extractor, how to design a classifier that will classify the fish to its correct class, right? and we try to have as minimum error as possible. So for this, to make the machine have this ability, we have to show them certain training examples as well, right? Because if the machine will see that, okay, this is a C bus looks like this and Salmon looks like this, then only that will be able to learn their patterns, and then they will be able to classify an unseen fish as well, right? So let's say we have a set of training examples. These are denoted as capital X1, Y1, and X2, Y2, and up until Xn, Yn. So we have n training examples. So these Xi's that you see is basically a d-dimensional feature vector, which is a list of numbers that we are getting from the feature extractor. And Yi's is basically the label of the features of the ith fish, right? So yi is basically a sea bass or a salmon. But since we are designing algorithms that would use maths, so let's not keep it categorical. We will convert them to numbers, right? So let's say yi is a 0 and 1. A 0 stands for sea bass and 1 is for salmon, right? So now our problem at hand is we want to construct a decision rule for classifying an unlabeled fish with feature X to one of the two classes. Right? So to solve the problem, we will use statistical learning theory to develop classifiers. Right? What is this? Now see, every sea bass is not same. Their features will not be same. Every salmon will not be same. So there are variations in the features of a particular species, right? Now, statistical learning theory helps us to model these variations in the features by using probability models. Right? So, this is nothing but an approach where we will express the variability in the features of different species through probabilistic models. Right? Suppose in our training data, you observe that there are as much sea bass and salmon, so they are all 50-50. So, intuitively, we would say that the next fish is equally likely to be a sea bass or salmon, right? More generally, we assume that there is a prior probability that the next fish is coming is what? Either it's a sea bass or a salmon, right? So our first and simple classification rule can be based on these prior probabilities as well. So these are nothing but a way to reflect our prior knowledge of how likely we are to get a sea bass or a salmon, right? Before the fish actually appears. Now, if we only make a decision with such little information, it seems logical to use following decision rule, but only for one classification. For example, let's say you have 100 fishes, out of which 70 are sea bass and 30 are salmon, right? Now, if you have to classify one unseen fish, you say that okay, it's likely that 70% of the times the fish is sea bass, so let's classify it as sea bass, right? So for one classification, this classification rule seems logical that whatever has a greater prior probability, we will assign that class to that fish. But when you have to make 5,000 predictions, every time you will end up making the same prediction that it's a sea bass, and you know that both kind of fishes can appear, right? So this uh, decision rule has an issue as well, right? And further, we are not using features of the fish before deciding its type. So these are two issues that needs to be tackled. So this decision rule was quite simple, but there are issues, so we have to improvise on that, right? So before going to the next one, just want to check: is my pace all right, Shatik, or am I good? Is it very fast?
Yes, yes. No, no, no. It's
Yeah,
perfectly all right.
it's fine, right?
Anyone having any question till now? So if you have any, you can just ask him. Yeah, please go ahead.
Okay, thanks. So this simple decision rule will not work when we have to classify multiple fishes. So, given that there are truly differences between the population of these two fishes, we view them as having different models, right? Or specifically different probability models. Since their descriptions are different, and we try to model them mathematically through different probability models. Now we will denote the probability density function of feature vectors of class I as Fi. So these are nothing but the class conditional densities. What are these? I'll explain. See, the response variable here, response variable means the class labels, that whether a fish is a salmon or a sea bass. The response variable here, that is y, has two discrete values, right? That is 0 and 1, since we have done the encoding. So we consider x to be a continuous random variable whose density function depends on the class y, expressed as f of x given y equals to I. So given class I, the density function of the feature vector is basically f of I. I hope the notations are clear. These are called class conditional densities. Now we will use the prior probabilities and the class conditional densities to design a classifier. So we define a new quantity, that is qix, that is nothing but the likelihood that given a fish, what uh, that given we have a fish, what is the likelihood that it belongs to class I, right? So this is nothing but the probability that the class label is I given the feature vector x.
So basically, sorry for interrupting. X is
Yeah,
the feature of the fish, and it is given. So given that,
yeah, it's
what is the
given,
probability that it's a salmon or a sea bass, right?
right?
Okay.
Okay. So now what we do is we just break it into uh so we just a second. Yeah. Yeah, so we just simplify this. So this is simple law of probability. P of A given B can be written as P of A intersection B divided by P of B, where A and B are given events. Now we again write the numerator as a conditional density, where we now basically condition on the class, that given it's a class, what's the likelihood of the feature vector, right? And in the denominator, you see it's just the law of total probability that's uh, there. And according to our notation, this is what we get, right? So this is nothing but a simple application of Bayes rule uh, that you have learned. Now we will design a decision rule where we will assign class 0 if the feature vector x is more likely to come from class 0 rather than class 1. It seems very logical, right? So our classifier, we denote it by h of x, that's 0 if q naught x is greater than q1 x. This is a very simple rule of classification. This is what is called the Bayes classifier. This Bayes classifier maximizes this Bayes classifier actually minimizes the probability of error, right? It, and in this sense, it's an optimal classifier, right? What is the probability of error? Probability of error is basically the chances of making mistakes, right? Mistakes are if a fish is sea bass, you're saying it to be salmon, and the other way around, right? So this classifier tries to minimizes. So this classifier minimizes the probability of error, right? Now, in this classifier, we are making an assumption that the cost incurred in misclassifying sea bass as salmon and vice versa is same, right? Now this might not be the case always, so the algorithms needs to be changed accordingly. So we have to do it, but again, for the sake of time, we are not going into details of how to change it. But yes, if the costs are different, then the algorithm will change accordingly. I can give you an example how it's possible that the costs are not same. For example, suppose you are designing a classifier to detect whether the coming aircraft is an enemy aircraft or it's a friendly one, right? So there can be misclassifications. So if you're misclassifying an enemy aircraft to be a friendly one, that's very dangerous, right? So the cost incurred is very heavy, because if you have an enemy aircraft and you if you classify it to be friendly, it can destroy your entire base. Whereas if you have a friendly aircraft, you classify it to be as an enemy aircraft, everybody will just have to move to a bunker, right? So the costs are not same of misclassification. So when the costs are different, you have to design it differently. But for the sake of simplicity, we have assumed that the cost incurred in either type of misclassification is same. Now, for implementing this classifier using a set of data points, we need this prior probabilities and this class conditional densities. The functional form of them must be known, otherwise we won't be able to implement them, right? But in practice, it's hardly known, so we need to estimate it using the training data. Now, just to keep in mind, the Bayes classifier was optimal. It was the best classifier that can be designed, but since class conditional densities and prior probabilities are not known in advance, we have to estimate them, and in estimation there are chances of errors. So now the Bayes classifier will lose its optimality, right? So there are two ways to estimate the density functions: parametric and non-parametric. I guess the audience is aware of the difference between the two methods. For today we will dig deeper into the non-parametric methods of estimation, right? So we'll try to implement the Bayes classifier using a non-parametric method. So for implementing this, we just need to get hold of P0, P1, F1, and F2. If we are if we get these four quantities, then we are done, right? So we will estimate these things. So the prior probabilities for the ith class, that is Pi, this can be estimated as just the ratio of the number of training samples in the ith class to the total number of samples we have, right? This is an unbiased estimator. This is a very simple one. Apart from this, now the problem boils down to that given we have some IID draws from some distribution, we need to estimate its PDF, right? So for simplicity, we are considering feature vectors to be one dimensional. The same ideas can be extended to multiple dimensions as well. So we'll start with a very simple thing to do. Let's try to learn a piecewise constant approximation to the density function. So let's say the density value takes a constant value k over an interval a to b. Now probability that x lies between a and b is nothing but the integral of fx dx that runs from a to b. That's nothing but k times b minus a, right? Or k is basically the ratio of the probability you see divided by the length of the interval, right? Now if we want to estimate f, we just need to find an estimate of k, right? So finding estimate of k means we just need to estimate the probability that a lies between x, that a less than equals to x less than equals to b. Now these can be estimated by the fraction of data points that fall in the interval. So a very simple estimate is f dash that f hat x is basically m upon n b minus a, where x belongs to that interval and m is the number of training points in the interval a to b. It should be a to b, sorry. So we can approximate f by the histogram of the data. Now the quality of approximation depends upon the size of the interval. What size we are considering. We can get better approximations by increasing the number of bins or having finer intervals. So the more smaller the intervals are, the better are the approximations. Now, there's one problem with this. If we extend this idea in d dimensions with n bins, so for 2 dimensions we will have n cross n, that is n square bins. For 3 dimensions we will have n cube bins. For d dimensions we will have n to the n raised to the power d bins, right? So the number of bins grows exponentially, and this is a problem. Why? Because because in that huge feature space, you will not find enough examples in all the bins to find a proper estimate of f, right? So this is what is called the curse of dimensionality. However, there is a solution to this. We can make this idea work if we erect bins only around training examples. So let's define an region bx, that is a ball of some radius around x. And what the radius is, it's a basically a hyperparameter that can be tuned. So let it be some arbitrary number r, and now we will go
Sir, sir, concept of beans is not understand.
concept.
Please repeat.
Yeah,
Beans.
okay, sure. I can tell you like this. Wait. Okay, so basically what bin says. Okay, wait. I can just when I can. Okay, I will tell you. See, what basically we are doing is we are having a one-dimensional space on which we are having some training points, right? And we want to estimate the density of f, right? So basically, what we do is we divide the entire space into bins. We will divide it like this, and
It
we
is a concept of partition in integration.
will. Yeah, so creating bins is basically partitioning the feature space only. Yeah, but integration, I don't understand. You don't need to link it to integration. It's just in the feature space we are
Uh-huh.
creating small areas, and we will estimate the density over here by erecting a bin that is basically a histogram that is nothing but the number of points in this area, that is 4 divided by the total number of training samples that we have. So it's 4, 10, 11, right? So this will be the uh, estimate of the density function at for all the values of x lying in this particular interval. Okay, so this is a constant approximation. So this is what we are doing now. If we have a two-dimensional feature space, we will, and if we create 10 bins for x and 10 bins for y, so total we will be having 100 bins, right? In d-dimensional, that would be n to the power d bins. So this is what I'm trying to say.
Okay. You divide the small sub interval and into smaller to smaller.
Yes, so basically the length of the interval should go to 0 to get very
Okay.
good approximations, right? But as
Yes, yes.
we
N tends to
as
zero.
yeah, but as we decrease, no, not n tends to 0, the length of the interval should go to 0, right?
Okay.
So the number of bins will increase. So uh, the more smaller intervals you have, the better approximations you get, right? So that is the entire idea.
Okay, sir.
Just a second. Any more questions on this? I hope no. Just a second, guys. Let this start. Let me go over it again. Just a second. Okay. So we discussed till the curse of dimensionality. However, this idea can be made to work if we erect bins only around the training examples, right? So what we do is we define a region Bx, a ball of same radius around the point x where we want to estimate the density, right? So we define rho, that is nothing but the integration of uh, f over the area bx, right? And since this fs since this the density function is taken to be nearly constant over bx, then rho is nothing but the product of fx times v, where v is the volume of bx, right? So from this, fx is approximately equals to rho upon v. Now, suppose out of this n IID training samples that we have, there are k samples that are in the region bx. Then k is nothing but a binomial n comma rho, right? So k can be approximately taken to its mean, that is n times rho, and you get an approximation of rho as k upon n, right? So you can estimate rho as rho hat, that is given by k upon n. And by doing this, finally you will get an estimate of the density function at the point x, that is k upon n times v. This is the basic idea of fitting an approximation of f in a non-parametric method of estimation, where k is the number of points in the region bx that is centered around x, and v is the volume of that region, and n is the total number of training points that you have, right? So but the problem is still unsolved. We wanted to get an estimation of f, but again we do not know k, we do not know v, just we know n, but this will not work. So again there are two methods of solving this. So what we can do is we can first fix the volume v and then find k, that is the number of points in that volume.
Kaushik, sorry for
Yeah,
interrupting. What do you mean by volume here? Can you just repeat again?
yeah. So
How
volume,
are you defining volume?
yeah, the volume is basically the area of the ball that we are. So the volume is the volume of bx. Bx is a ball of some radius centered around x.
Okay, 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 got it,
Yeah.
got it.
So now this f hat can be found out using two methods. What we can do is first we can fix v and then we can find k. So this is nothing but the Parzen window estimate or the kernel density estimate, right? Other way around, what we can do is we can fix k and find v. This is result in a k nearest. This will result in a k nearest neighbor estimate that we'll look at, right? So for doing this, let's define a function phi of u. Now we are looking at the first one where we are fixing volume and then we are trying to find k, right? Now you have to understand this function a bit. So phi of u is basically an indicator function if all the elements of that vector are less than equals to zero point 0.5, right? So if you imagine it for two dimensional, you will get that it's nothing but it's 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 a cube of length 1, right? And similarly, if you think for d dimensions, it's a hypercube in r to the power d centered at the origin, right? Why we are defining this, I'll tell you. So if we do a scale and origin shift, phi of u minus u naught upon h would be nothing but a hypercube of side h centered at 0. This is just we are changing the origin and the scale to get a hypercube of a particular uh, side length h and a center u naught, right? Now for any data point x, phi of x minus xi upon h would be 1 if xi falls in a hypercube of side h centered at x, right? So now we are looking at the phi of x minus xi upon h. This would be 1 if the point xi falls inside the hypercube where the side length is h and which is centered around x, right? So the number of data points falling in a hypercube of size h centered at x is basically k. So we sum all the indicator functions to get the number of points, right, for each of the i's. The Now the volume of the hypercube is h to the power d, since it's hypercube. So for two dimensional it's h square. So similarly you can think in d dimensional is it's h to the power d. So what ultimately we are trying to do is we are fixing a volume that is h to the power d, and we are calculating the number of points, number of sample points, or number of training points that are there in that particular volume, right, in that particular area centered around x. And what is this x? This is the point where we are trying to evaluate the density, right? So the density estimate is now given upon is given by 1 upon n, and the summation of the total number of points falling inside that particular area and divided by the volume, that is h raised to the power d. I can go back once. You can see that you can see that f hat was nothing but k upon n times v. So now the volume is h raised to the power d, and k is nothing but the number of points that are falling in that volume centered at x, right? This is known as a Parzen window estimate. But again, there are some limitations to this as well. The density function is basically a continuous function, right? So that has to sum up to 1, and that's greater than equals to 0. Now there are many discontinuities if we try to estimate it like this. Now this problem can be made away by changing the function phi, since we have introduced phi as a hypercube of side h centered around the test point x, for which we are trying to estimate the density. If we change the form of phi, we can remove the discontinuity problem, and we will get a continuous and we will get a continuous estimate, right? Now these estimates are good enough because they are consistent estimates, but how we will h, that's a problem because we haven't discussed about that. So basically you have to make sure that as n tends to infinity, the volume has to go to 0, and n times the volume has to go to infinity, right? Why this is necessary? This is necessary for the consistency of the estimate that we have derived above, right? But again, the consistency proofs are a bit involved, but yes, these are the conditions that needs to be made sure before deciding how h should look like. So can be h can be taken as 1 upon root n, right? So ultimately the conditions will meet, and you will get a consistent estimates as well. So this is what Parzen window estimate is. And if you replace phi with some density functions, you will get what is called kernel density estimates. Now we will look at another problem that will fix volume. In the previous one, we have fixed volume and we were trying to find out k. Now what we will do is we'll fix k and we'll try to find the volume. For this, I'll introduce the problem once again, as we are dealing with a two class problem with some prior probabilities PIs and class conditional densities FI, right? This was the problem. We need to estimate we need to implement the Bayes classifier. For that we needed the class conditional densities, the estimates of the class conditional densities, right? So what the feature vector that is given by f of x. Now suppose we have n data samples, n naught and n1. So you can understand this n naught is basically the number of samples belonging to class 0, and n1 is the number of samples belonging to class 1. Now to estimate f, we do a k nearest neighbor estimation procedure, right? Suppose the needed volume is v. Suppose in this volume there are ki samples of class I, right? Equals to 0 to 1, I equals to 0 and 1. Now you may ask that why, uh, l- like how can we estimate this volume, or what's the fixed value of volume that we need to take, because you said that volume is fixed and we are trying to find out k. But don't worry, this volume will cancel out later on while implementing the Bayes classifier, so it won't matter, right? So let's say we define a volume v, and in this volume there are ki samples of class I. Now using the same volume estimates, we estimate density functions f as well as fi's by using the same method that we discussed previously. We have fi hat given as ki upon ni times v, and f hat is given as k upon n times v, right? And the estimates for priors would be again ni by n for the ith class. Now using this, we would like to estimate using this we would like to implement the Bayes classifier. So for Bayes classifier you need qjx. If you remember this, that's nothing but fj times pj upon f, and we just put in the values and we'll get kj upon k. And our Bayes classifier was to put x in class j if qjx is greater than qix for all I. That is nothing but kj is greater than ki. And this is what nearest neighbor classifier is, right? And what so basically nearest neighbor classifier is nothing but Bayes classifier implemented using the k nearest neighbor estimation procedures of the class conditional densities, right? And hence it tends to work very good, because since Bayes classifier is the optimal classifier, it's the best classifier that you can ever have. If we implement Bayes classifier using estimating by estimating the class conditional densities uh, using the k nearest neighbor rule, this is the estimator that you get, right? And I would just like to repeat once that what nearest neighbor classifier is. Nearest neighbor classifier is, for example, if you have a point which you need to classify, you define the k nearest neighbor points. You just find the k nearest neighbor points and assign the class that is the majority class there, right? For example, if you have a point and around that you're looking at 5 closest points to it, so closest 3 are c bars and 2 are salmon, so you will assign that test point to be as c bars, right? So you decide classes by majority voting, and this is what is happening here. As I said, this is nothing but the Bayes classifier implemented, where the class conditional densities are estimated in a non-parametric fashion using the k nearest neighbor estimation methods. Now, a very interesting fact to know, that if we have a sequence of IID examples, asymptotically, the probability of error by nearest neighbor rule that we have derived now is never more than twice the base error, right? So as you know, the base error is the minimum error that you can have, right? And nearest neighbor rule will never have an error more than twice the base error. So this is a very important result. Again, the proof is much more involved and complicated, so we'll not go in any proof. But yes, if we have a sequence of IID examples, asymptotically this rule holds. That is, if the accuracy of the Bayes classifier should have been 95%, then the accuracy of the nearest neighbor classifier would be at least 90% that we would get, right? So this is a very useful thing, because in a classification problem, this is the first thing that you can try. So nearest neighbor classifier is usually used as a benchmark as well. This performs really, really well. This should be applied at first as without doing any work, right? This is a very simple algorithm to do, and you do not need anything very complicated and very fancy to implement this. Yes, now one question arises, that how do you find the closest point? So there needs to be a notion of distance matrix that we are using. So that depends. There is a discussion on that, but again, if you s- if you fix that how you're calculating the distances, then finding the nearest points should not be a very challenging task, and implementation is fairly simple. and you will get a very nice accuracy with this as well. Now again, there are few more problems with this classifier as well, because this is a storage heavy kind of a classification rule, because you need all the training samples with you at the time of classification, right? So the memory becomes a problem, the storage may become a problem when you are having large training sets and you are having a large number of test samples as well, which you need to classify. So that's a problem again. But yes, on the front of accuracy, its accuracy is good enough, and its error is not more than twice that of base error. So this can be a first thing to implement. Now I will somehow rephrase the problem that we were considering. Let's say we are having some training examples, xi, yi, and we are having n training examples, and our task is binary classification problem that we were considering beforehand also. Each of the feature vectors xi is a d-dimensional vector, and now I am changing the notation a bit. Let's say these class labels yi are no more 0 and 1. I'm changing it to -1 and 1. Why is this done? You will see in a few slides, right? So now we are considering a following classifier that you can see. The hx is 1 if gx is greater than 0, and it's -1 otherwise, right? Now g is called the discriminant function. If we choose gx to be q1x minus q0x, then this is the base classifier, right? This is what we have discussed till now. If you just take gx, the discriminant function, to be q1x minus q0x, then the classifier says that classify it to class 1 if q1x is greater than q0x. And again, we are calling the class 0 as class -1 here, right? That's for notational convenience, but again, I hope you understand. Uh, this is nothing but the base classifier. So we are looking at a method of building classifiers where instead of learning the class conditional densities, we instead assume a functional form of G and we learn the needed function, right? So now we'll not consider the class conditional densities and all that stuff. We will just assume a functional form of G and learn the needed function, right? Suppose G is specified by a parameter vector W, that is again a d-dimensional vector. Uh, the linear discriminant function we are assuming here, you can see it's nothing but W transpose X plus B, where uh, W is the parameter vector, it's a d-dimensional parameter vector, and B is the bias term, and X is the feature vector. This is known as the linear discriminant function. Linear in parameters, again, this is something to take care of. This is not linear in x's, this is linear in parameters, right? So this is a linear function. Now we are trying to learn this linear function, and we'll use our training samples to learn the best linear function possible. Are there any questions here before we go on to the next slide?
I guess not. No.
Okay. Okay. So the classifier can be written in a very simplified form, where you can see it's nothing but the sign of W transpose X plus B plus 1 upon 2, right? So now suppose you have a training set which is denoted by red points, and you have some green points. These two different colors represent different classes. Now we want a linear classifier. Now again, a linear classifier in D dimension is nothing but a D-dimensional hyperplane that passes that would classify these two classes. Now there may be many such linear classifiers that would perfectly classify these two sets of different points. right? There are in fact infinitely many perfect classifiers, but which one should we choose? It's better not to select a model whose decision boundary passes very close to a training point. You see, these decision boundaries are basically passing very close to training sets, right? And again, the training set that we have at hand is basically a part of the entire population, right? So for different persons having a different training set with slightly different examples might have a green point here as well, might have a red point here as well. If we choose a decision boundary to be very close to our decision, to our sample points, then the decision boundary that we will create will be very specific to the particular training set we have, and it would fail to generalize very well, right? And that's the ultimate aim that we are having. Based on the training set we have, our classification rule or the decision boundary that we tend to create should be robust, should be as robust as possible to the training set we have taken, right? So as I said, the models having decision boundaries very close to some training points is not good. These are not robust and might misclassify test data, right? Predicting the wrong class. Whereas we will try to have a decision boundary which s- separates the classes as clearly as possible, right? That is as far as from the training samples. So basically we want two things from the classifiers, right? Every point should be classified correctly. This is the first criterion that we would like to have. This can be ensured if the sign of a W transpose xi plus b, that was our linear classifier, is basically equal to the class labels, right? Because this was the definition of our and classifier. If the sign of W transpose xi plus b is plus 1 for xi belonging to the class plus 1, then their signs are equal. And if xi belongs to the class negative 1 and the sign is also negative, then these two are equal. So we are having correct classification, right? In either cases. Or equivalently, if you multiply these two things, so if y is negative, this should be negative. If y is positive, this should be positive. So if you multiply two quantities having same signs, you always get that to be greater than equals to 0, right? So this is another way of writing the same thing. Second, what we want is that uh, our decision boundary should be such that training point the closest point that we are having near to the decision boundary should be as far as possible, right? So now, uh, another thing, the distance of a point from a hyperplane is defined by this. So let's say if you have a point P and you want to find the distance of a hyperplane parameterized by W comma B, then that is defined by W transpose P plus B upon the L2 norm of W. So this can be proved. This is a very simple geometry. But yes, so now what we want is the minimum of these quantities for all the training points. That is the minimum of W transpose Xi plus B upon uh, the L2 norm of W. That is the distance of the closest training point from the decision boundary should be as large as possible, right? So we want to maximize this complete quantity subject to the fact that we are having correct classifications for all the points. I hope you understand this. What we are trying to do is we are trying to find a decision boundary. And what do I mean by finding a decision boundary? I mean to find a W vector and a bias term which will create a decision boundary which will classify all the points correctly. So our first point will be satisfied. Apart from that, the decision boundary will be as far as possible from the nearest training point. I hope this is clear. I will repeat it once more. So basically, x's are the training points. We calculate the distance of the training points from the decision boundary parameterized by W and B. We tend to calculate all the distances. We take the minimum of that. So we are wanting to have the minimum distance should be as large as possible, so that the separation is as clear as possible, right? So now we will write our objective function that will satisfy these two conditions. So basically we need a linear classifier that perfectly classifies the trained data while keeping data points as far as possible from the hyperplane, right? So a requirement can be written as I have said you, we want W and V. So we are maximizing the minimum distance of the training point from the classifier, right? So W transpose Xi plus B upon mod of W was the distance of the point Xi from the hyperplane parameterized by W and B. We are looking at all those distances. We are taking the minimum one. So we are looking at the closest point to the hyperplane. Now we want this closest point to the hyperplane to be as far as possible. So we want to maximize this again. And what is our condition? That the classifications should be correct. That is, yi uh, times W transpose Xi plus B should be greater than equals to 0 for all the training samples. I hope the objective function is clear. It's just two things that we are trying to do. We are subjecting to a condition that we should at least classify all the points correctly, keeping the closest point as far as possible from the hyperplane, right? So this is the objective function for support vector machines that we need to solve. Again, solving this is not a very simple vanilla thing. It's a bit more complicated. For the sake of time, we cannot go into the details. But anyways, so this is a constant optimization problem. By some rewriting and some manipulation, this optimization problem could be expressed as this one, as you can see here, right? By some mathematical manipulations, you can see these optimization, these objective function can be written as this. And again, our consideration for this is that we take a training set that is linearly separable. There are training sets which are not linearly separable, so that again becomes a problem, but we are not taking that for now. For now, assume that the training set is linearly separable. Provided it is, we can rewrite the objective function as this one, right? And where this and where does this objective come from? We just had two requirements, right? That every point should be classified correctly, and the closest point to the hyperplane should be as far as possible, so that we will have a very clear separation, right? Now again, one more thing that's very interesting and useful. This parameter, this parameter, this uh, the uh, parameter vector W can be written as a linear combination of the training samples, right? This can be written and this can be proved. There is a theorem called the representers theorem that establishes this, that the parameter vector W is nothing but a linear combination of the training samples itself. So if you guys are familiar with linear regression problem, you have seen that that the MLE estimate of the parameter vector is nothing but the uh, so basically the estimate is x transpose x inverse x transpose y. So again, it's basically a linear combination of the training samples only. If you're familiar with gradient descent algorithm, with the optimization algorithm gradient descent, you have seen the steps. So basically the steps are also, if you try to formulate it, it's somewhat the linear combination of the training samples only, right? So this is a, again, this is a justification, a short justification, but again, the complete proof is beyond the scope. And we will assume that the parameter vector can be written as a linear combination of the xi's, and we and these alpha i's are basically constant. And what you see is, if you go deep into this, then the optimization problem again can be rewritten in terms of alpha i's, right? Now, just one more thing. This parameter vector is summation of alpha I times xi. This alpha i's are again constant. Since yi's are also -1 to 1, you can just multiply them and it will change anything, because the constants will change accordingly, and you will find them through the optimization methods that we are doing. So we can have w to be expressed as this. This is a very important step. You will soon realize why. Now w, as I said, it's the summation of yi times alpha I times xi. So it's nothing but the linear combination of the training samples. Now we want to solve the optimization problem that we had. This was the rewritten optimization problem. Now note this objective function w, the so the objective function here can be written as this. So this is nothing but w transpose w, and when you multiply this together, you will have a double summation, and you will have yi alpha I xi transpose yj alpha j xj transpose. Now these all are constants, constant yi yj alpha I alpha j. You will just have these two quantities, c xi transpose and xj. When you write it together, this is nothing but the inner product of xi and xj, right? So my point is that we started with uh, having a linear classifier. We wanted to classify all the points correctly. We wanted to have the decision boundary as far as possible from the closest training point. And now we have also seen that the parameter vector can be written as a linear combination of the training samples. Now what we are seeing is the objective function is nothing but a summation, or a linear combination of the inner product of xi's and xj's. So basically, in this objective function, wherever there is xi and xj, they are appearing as inner products only, right? So this is a very important thing to note. This forms the basis of support vector machine and why they tend to work very good. So these are nothing but inner product between the two feature vectors. Similarly, now look at the condition that we were having. The condition says these yi times w transpose xi plus b should be greater than equals to 1 for all i's, right? So if you simplify this a bit, put w to be the linear combination of xi that as we have discussed, and you see once you multiply them, again you get xj transpose xi, and this is nothing but the linear product of xj and xi, right? And this is summing over j. So this is very interesting that in the entire uh, optimization problem, wherever you have the training samples, they only appear in the form of inner products, right? Now SVM is a linear classifier basically, right? So if your if your training samples are linearly separable, SVM will find a very good linear decision boundary that would classify it perfectly. It would be great. But very often the samples that we have are not linearly separable, right? To learn non-linear decision boundaries, we have to work with higher dimensional features, and they are really helpful. In the next slide, I have a video where you will get a flavor and see why we cannot find a linear decision boundary in a lower dimensional feature space, but once we get to a higher dimensional feature space, we will be able to fit uh, linear discriminant functions well, right? Now, as I have told you, the complete objective function or the complete optimization problem in SVM can be written in terms of xi and xj's through their inner products only. Now, if we have to deal in higher dimensional feature space, then we have to calculate these inner products, right? And xj's and xi's will no more be in their original in their original dimensions. Their dimensions would increase since we are make since in a high dimensions, since to go in a higher dimension we are making certain transformations. So if we have certain way to calculate these inner products efficiently, then we are through. Then we can implement the algorithm in very high dimensional feature space, in fact in infinite dimensional feature space as well. And we can get very non-linear decision boundaries. We can be able to separate training samples having very complex and non-linear decision boundaries as well, right? So the ultimate thing is that the objective function can be written in terms of xi's and xj's through their inner product only, and we have a way where we can evaluate these inner products in a very efficient manner, right? And this is where the kernel trick comes to rescue. The kernel trick will help us to do this. It would help to evaluate the inner products very efficiently. I will play a video and you can see this. Yes, yes. Just a second. It's okay. So now see, the problem is that this is the feature space that we have. There are certain blue points and there are certain red points. You can clearly see that there is no linear way to separate them easily, right? We cannot draw a line and separate 2 points as we saw images earlier, right? So now what will happen if we project these two-dimensional training samples to a three-dimensional space, right? So now you can see, now you will have a hyperplane that can separate these two sets of training samples. So basically we are doing nothing, but we are fitting a linear classifier only, but not in the original feature space, but in an projected feature space of much higher dimension, right? The data which was not linearly separable in its original feature space becomes linearly separable in a higher dimensional space. And when you project it back to the original space, it becomes a non-linear decision boundary. So this is the complete point that I was trying to make. Uh, this is what SVM does in a very efficient manner. So what we do is essentially we consider a mapping X. So X was our original feature vector. We transform that to another feature vector phi of X, where X may be 1 or 2 dimensional and phi of X may be 100,000 dimensional or even infinite dimensional, right? But you will say that okay, in the optimization problem we needed to multiply and calculate all those things, xi transpose xj. Now if that is infinite dimensional or 100,000 dimensional, the 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 time taken to do that computation will be infinite, right? So that was a problem, but that is not the case. That's the magic here, that even if your original feature space is very low dimensional and you project it to an infinite dimensional space, the algorithm works and the computations are really fast, right? The computations can be done in 1 or 2 dimensional space without calculating calculating the vector of 100,000 dimensions, right? And the results will be same. So that's the trick. The results would be same, but ultimately you will be doing the calculations in very low dimensions only, right? So what we do is we project this x, these feature vectors x, to a high dimensional feature vector phi of x. These computations of the inner products are basically done via kernels. So this phi, as we are looking here, it's basically a map from d dimensional, the original dimension, to a very high dimensional feature space. It's basically a nonlinear map. Since phi is a nonlinear map, our classifier W transpose phi of x will look nonlinear in the original feature vector x, as you just saw in the video. We used and we will use linear machine learning algorithms in the higher dimensional feature space. So basically, the kernel trick allows us to learn some very special nonlinear maps to run machine learning algorithms on the extended feature vectors without even computing those vectors explicitly. See, now what will happen is we were supposed to calculate the inner products of xi and xj, right? Now, if these xi's and xj's are projected to a very high dimensional feature space, then we basically need to compute the inner product of phi of xi and phi of xj. This is what we were supposed to do. For this, we have to multiply this, right? So the inner product is basically phi x transpose times phi y. So you have to compute this, and the computation will take some order. Uh, uh, so and the computational time taken to solve this will be almost infinite, but that is not the case. The result what we will get by solving this is same if we apply the this function k on these two vectors xi and xj. For example, I can show you that with an example of a quadratic kernel. Let's say there is a kernel function defined as this. So if you calculate these things, if you calculate k of x comma y, the result that you will get is same as multiplying these two vectors. This you can take as an exercise as well, where you can verify these calculations. So basically, if you expand this, you will get a vector that is phi naught x, phi 1x, and phi 2x, and this is basically a d square plus d plus 1 dimensional, right? If your original dimension of x is d, you extend that to a very high dimensional feature vector, that is d square plus d plus 1 dimensional feature vector, right? And you, for performing the inner product, you do not need to do the computations in this high dimension. You can just calculate this function and you're done, because the results will be same. Computing this thing and multiplying these two vectors together will give you the same result. And why? You can just expand this and you can check the calculations to get this, right? You can take this as an exercise as well. So we can say that we want to work with high dimensional feature vectors, and when the machine learning algorithms asks us for dot products, we will just provide the kernel function, right? We will not do the computations in this high dimensional. We'll just provide the kernel function, and the machine learning algorithm will work. So this is called the kernelization of all the algorithms. In fact, linear regression, logistic regression, k nearest neighbors, these are all kernelizable things, right? You can kernelize all these algorithms, right? And they will work fine. So they will work. So these all things will, these all algorithms will learn a linear decision boundary in an extended feature space. But again, when you have them in the original feature space, the decision boundaries will look nonlinear, right? And you do not pay any cost of extending them to higher dimensional space, because the computation time and resources need not uh, uh, so basically the computation time and resources are not required according to the higher dimensional. It can be done in the original dimension only, right? So the time complexity does not changes, and this is because of the kernels that we have, the kernel functions that we have. Again, all the functions cannot be written in this form. The kernel functions that can be expressed in this forms are known as Mercer kernels. So there are special type of functions, but yes, they can be used, right? So the ultimate crux is we would get same results as working directly with phi of x, but without having to compute phi. This is how we learn non-linear decision boundaries using SVM. Right. Again, there are a lot of mathematical details involved, but again, due to time constant, we cannot go in that. But yeah, this is the overall picture what SVM does, and some basics of estimation through non-parametric approaches, where we tend to estimate the class conditional densities, and we get the nearest neighbor classifier. Yes. So this is it. I think if you have any questions, you can go ahead and ask.
Yeah, so if anybody has any question, they can ask. And I have just uploaded one form in the message. So you can just go and give a quick review of the seminar. How did you like it? Kaushik, if you can switch on your
Yeah,
video
yeah,
maybe.
yeah.
Yeah,
Am I visible? I guess yes.
yeah, you are, you
Yeah,
are.
yeah.
So yeah, thank you so much for that wonderful session. It was very informative, and yeah. So if you guys have any question, you can ask him, and I will give you guys his email ID. Is it okay, Kaushik?
Yeah,
If
yeah,
I give
sure. You
your
you can
email ID?
you can give a way to contact me. In fact, I will share the slides with you. You can share them with everybody.
Sure, sure, sure,
Yeah.
sure, sure.
And if somebody
Okay.
has any questions now, you can ask as well. That's fine.
Yes. Okay. I guess they don't have any question. Okay. So yeah, it was wonderful having you today, and yeah, hope to see you soon.
Thanks for giving a chance to present. This was my first seminar. So thanks a lot.
You did great. You did great.
Thank you.
Yeah. Okay. Okay, Kaushik. Bye. Bye, everybody.
Bye. Bye.